So, now I'm going to talk about the solar system, its origins, what's in it, that sort of thing. So, first off, how did the solar system form? Well, it would have been something like this. It started in a nebula, the remains of a dead star, a huge cloud of gas, and various materials left over from when an older star went supernova and exploded. And in this nebula, some gas came together and formed a star, a new star, our sun. And its gravity started influencing the dust and gas around it. What originally was just like a big cloud of gas all around the sun, due to certain quirks of the way angular momentum and stuff like that works, compressed into a disk around the sun's equator, sort of like Saturn's rings. And in this disk, which was, more compact, it was easier for things like planets and asteroids and stuff to form. Again, through just things incrementally hitting each other and getting bigger and getting more gravity, stuff like that. So, the early solar system is very chaotic. A lot going on, a lot of stuff crashing into each other, but over time, a lot of stuff crashed into other stuff, or fell into the sun or some other large object, or got ejected from the solar system, and now the solar system has kind of calmed down into a more stable situation, and so that's what I'm going to be talking about. So, what is the solar system? The solar system is just the region of space dominated by the sun's gravity, basically. So, at the middle of the solar system, we have the sun. It's big. It's a star, which means it's made up of primarily hydrogen and helium gas, and that it shines because its gravity is so strong that it can achieve nuclear fusion in the center, which produces a lot of energy, and that's why the sun shines. I'm going to go from the inside out in terms of the order I talk about stuff. So after the sun, we have Mercury. Mercury is the first of the inner or rocky planets, so-called because they're made primarily of rock. It's the smallest one. Mercury doesn't have a whole lot going on, to be honest. One of its distinctive features is that its day is really long. I don't remember exactly how long, but it's like a third or two-thirds the length of its year. And the reason that is because if, as you might recall from my talk on the moon, like how the moon is tidally locked with Earth, where it orbits Earth and rotates on its axis at the same speed, Mercury, due to the strong gravity interactions between it and the sun, is kind of like a third or two-thirds of the way to being like the moon is now. So it's getting there, but it's not quite there yet. Other than that, Mercury does not have a whole lot going on. No atmosphere. It's hot because it's close to the sun. Yeah, that's about it. So next up, after Mercury, we have Venus. Venus is sometimes called Earth's twin, because it's really close to the same size as we are here on Earth. It's a little bit smaller. It's about 90% the size of Earth, but still really close. Venus is notable that it's hotter than Mercury, even though it's further away from the sun. Why is that? Well, it's because of Venus's atmosphere. Venus has one. It's really thick, much denser than our atmosphere. And the reason that Venus is so hot is because of the greenhouse effect. Greenhouse effect is a pretty important concept. It's named after greenhouses, which are like buildings made of glass that are used to raise plants in. The idea is that the glass lets sunlight in, but inhibits the sunlight from getting back out, so that causes the inside of the building to heat up and be a better place for the plants to grow. In the context of planets, the greenhouse effect is where certain kinds of gases in an atmosphere are good at reflecting sunlight. And so this does mean that it's hard for sunlight to get in. It's likely that sunlight's going to get reflected as it's coming into the atmosphere, but if it doesn't, it's then very hard for that sunlight to get back out. So it stays in there, sort of like a blanket, and increases the heat. That is the mechanism that causes global warming on Earth, but Venus has much more intense of a greenhouse effect than Earth does. Still, same basic process happening in both cases. Venus has a lot of clouds. If you look at Venus, it's just kind of like a smooth cream color. That's clouds. And Venus also has a lot of sulfur compounds and a lot of acid in its atmosphere. It has all kinds of crazy stuff going on in Venus. Very inhospitable. We haven't sent very many probes to Venus because it's just really hard to build for a place that's so hot and acidic. The Soviets built a probe in the 80s, and it lasted for like 4 hours before dying. That wasn't a failure. They expected it to last for about 4 hours. So, that's kind of the situation with Venus. There's something in the news that's happened recently about Venus that's pretty interesting, but I'm not going to talk about that here in the interest of making these videos as concise as I can. Next up after Venus, we have Earth. Earth's pretty cool, I think. Has a lot of interesting qualities. For one, all planets, rotate around an axis. Right? That's like their day. And all of the axes that the planets rotate on are tilted a little bit off of kind of where you would expect them to be. Right? You'd expect it to be like this, but it's tilted a little bit like that, for Mercury's sake. But Earth's axial tilt is really extreme. It's way more extreme than most planets. And so, this also means that Earth experiences more extreme seasons than other planets do, because of the fact that seasons are caused by axial tilt, as you've probably learned before in this class. Earth is also notable for having a really big moon. Earth's moon is big. In absolute terms, it's one of the biggest moons in the solar system, like top 10, certainly. And in terms of, it's definitely one of the biggest moons relative to what it's orbiting. Right? Like, Pluto's moon Charon is bigger relative to Pluto than the moon is to Earth. But other than that, no other moon even comes close to being as big relative to its planet as Earth, as our moon does to Earth. Our moon's also very close to Earth, right? So this causes the Earth and the moon to have a very powerful tidal interaction, an exceptionally powerful gravitational interaction between them, which causes all sorts of interesting things. Now, the moon's history with Earth is actually really interesting. Most moons in the solar system, we think, were captured, which means that at some earlier point they weren't moons, right, like in the early solar system, but then they got captured by the gravity of their planet at some early point, and now they're orbiting the planet. And that's a perfectly good idea for most moons. But for our moon, right, when people started figuring out how this idea worked, they realized that our moon was so big relative to us and so close to us that it would be extremely difficult for the moon to get captured by Earth's gravity. It would have to be coming in at like just the right angle, just the right trajectory to not end up like crashing into the Earth instead. It was really unlikely that the moon could have been captured by Earth's gravity. So they were like, what's up? And then we did the Apollo missions, and they came back and they brought samples of moon rocks back from the Apollo missions. And we did tests on them and found out that in terms of a lot of like geological and chemical signatures, moon rocks seemed really, really similar to Earth rocks in a lot of ways. And so that was also weird. Like, why would that be the case? And for a while, this was like a big mystery, until someone came up with an explanation that's so good that explains all the weird things about the moon so well that now it's pretty much just like universally accepted. And that theory is that in the early solar system, a planet roughly the size of Mars crashed into the Earth, and in the process would have kind of instantly melted the Earth so that it's like all lava, and knocked a substantial amount of that lava off. And the stuff that got knocked off went into an orbit around the Earth and eventually formed into the moon. So the moon is formed out of material that used to be a part of the Earth. And it's like, this is a crazy, dramatic thing to happen, you know? But it does perfectly explain why the moon rocks are so similar to Earth rocks, and why the moon is so big, and why it's so close to us. It's all explained very nicely by this idea. So, yeah, like, that we're pretty sure that's what happened. It checks all the boxes. Earth also has life, of course, that's a big deal. But that's something I'm going to get to in a little bit later. I'm going to hold off on talking about life for now. And I'm going to move on to Mars. Mars is pretty small. It's bigger than Mercury, but significantly smaller than Venus or Earth. It's well known as the red planet. The reason it's so red is that it has a lot of iron in its dust, and the iron kind of rusted, so it's like red because there's a lot of rusty stuff in its dirt, which is pretty cool. Mars has big polar ice caps with ice water, a lot like ours. So that's interesting, right? And in fact, we think that Mars used to look a lot like the Earth, right? We have very clear images of like riverbeds and canyons and stuff like that on Mars. Formations that we can tell would have had to have been eroded and carved by rivers of running water on Mars's surface at some point in the past. There's no liquid water on Mars's surface today, but there had to have used to be that stuff. So where did it go? What happened to it? Well, we don't know for sure, but here's the leading idea. Mars does have an atmosphere, but it's very thin. Something like 100 times thinner than Earth's atmosphere. And we think that Mars maybe used to have a more powerful greenhouse effect that would allow it to be warm enough to have liquid water on its surface, running water. But it lost its atmosphere. Why? So the Earth, and this is something I'll get into a little bit later, has various layers on the inside. It's got the crust on the outside, and then it's got the mantle, that's like magma, and then that's like molten rock, right? And then inside of that, at the center, you've got the core, which is mostly molten metal, liquid metal, and some metal that isn't liquid. It's hot enough to be liquid, but it's just under so much pressure that it's solid anyway. In any case, all that metal is rotating, it's spinning around in the Earth's core, and that generates a big magnetic field. Now the sun is a very chaotic place, and sometimes the sun does what's called solar flares, where a little bit of the sun's material kind of gets shot off into high energy clouds that just shoot out through the solar system. Now, if a cloud like this, a solar flare cloud, were to hit a planet with an atmosphere, it could take a significant amount of the atmosphere off with it. Not enough to like totally get rid of the atmosphere at once, but over millions of years, millions and millions of years, planets are going to get hit by enough solar flares that they could do real damage to an atmosphere over time. But Earth's magnetic field is able to exert a force on those charged particles, and instead of hitting Earth head-on, they kind of get spun around and hit the Earth in the polar areas. That's what, like, Aurora Borealis is. It's charged particles from the sun lighting up when they interact with things in the Earth's atmosphere. But because they're only hitting in like these places, and they're hitting straight down instead of doing like a glancing blow past, they don't really get rid of that much of our atmosphere. They only get rid of a very small amount. But Mars doesn't have a magnetic field. We think it used to, because we can see evidence of pieces of Mars's crust that got magnetized when it used to have a magnetic field like ours. But we think that Mars, maybe because it's smaller than Earth, cooled down, and its molten core cooled down enough that it's not molten anymore, it's just solid metal. And so it's not spinning anymore, and so Mars doesn't have a magnetic field anymore. And when that happened, solar winds could just go to town on Mars's atmosphere, leaving Mars with the very thin atmosphere that it has today. So does that mean that there's no water on Mars? Not necessarily. There are people, credible people, who really think that Mars might have liquid water, just in underground aquifers, like what you might dig a well into on Earth. We have them. And they think that Mars might be able to have liquid water in underground aquifers, but not on the surface. It's too cold on the surface of Mars to have those. Alright, so I think that's a good stopping point for this video. Next, I'll start getting into the outer solar system.